codes. But one disadvantage is that this kind of model focuses only on linear relationship, and maybe it would be a little bit restrictive in some sense if we look at this kind of regression model. So the more recent idea was to develop nonlinear investigation in functional regression, and this was mainly my contribution to this topic to investigate the non-parametric aspect in for instance, regression model here. And the only hypothesis, the only assumption that we can ask to the regression function R and P is to be regular in some sense. The continuous operator, Regression operator. So we go out the linear frame and we authorize our operator to be nonlinear. And then this is really a regression problem because this nonlinear operator has to estimate the conditional expectation. And the non-parametric aspect here is really linked with the nonlinear notion because we want to deal with nonlinearities in the relationship between the functional predictor and the response. A very simple estimator is the kernel-type estimator that we know for a long time in non-parametric statistics. But here, of course, we have to extend a little bit the kernel-type estimator with functional objects, and this is why we use a distance like K, which can be more generally symmetric. The function K is an asymmetrical decreasing function, and H is the bandwidth, which is a smoothing parameter, positive relying on positive relying. And then, of course, by using this kind of estimator, we can get, once again, prediction for the rest of it. So, the kernel-type estimator is very standard in parametric statistics, and its interpretation is also very simple because you can see the kernel-type estimator as a weighted average of the responses, and you have a weight which follow a very natural rule, which is closer to x is xi, and larger will be weight that you affect to correspond this response. So it is a very simple estimator. It's also very easy to implement it, and you can, for instance, use asymmetrical quadratic kernel. You can use also asymmetric, and this is for geometry an important point. You can use the F2 norm, but not on the curve themselves, but on their derivatives, because in geometry we have a problem of calibration, and it is well known that we have to derive the curves in order to get the good information for predicting responses, but we never know if it is the first or the second or the third derivative. This is why we use this kind of symmetries. Also, with a kind of cross-validation criterion, we can deduce the bandwidth, that is the smoothing parameter, and also the good symmetric that we have to use in order to implement the kernel-type estimator. And then you can get this kind of results, and I put on the right what the functional linear model provides, and on the left what the functional non-parametric model can produce. And you can see from the strictly mean square or prediction point of view, we can have a good improvement in comparison with the linear approach. The problem is that there is a big disadvantage for nonlinear regression model. I first start with the advantages. That is, this is really an exploratory tool in the sense that this is really a general model and it allows to capture nonlinearities in the relationship. This is also a flexible method because this is very local point of view when you have to estimate your operator around a fixed curve. You look around the fixed curve, what you can take into account, and so this is very local method which is controlled by the smoothing parameter and this edge, and you have also the choice of symmetry and so on. And of course, as we can see, this is a good predictive tool in the square prediction sense. And the implementation is also easy. But the problem of this kind of methods is that we have a loss of interpretability because when you deal with functional linear model, you can displace the functional parameter, but here you have no functional parameter. You have just an operator from functional space to where. So it's very hard to give interpretation of what is exactly the relationship between the function of the curves and the response. So the idea is to look for some interpretable while conserving some linear effect by quantitative learning. And we can, from this point of view, we can adapt very easy way this idea to functional data. So for instance, for the spectrometric curve concerning the mid data, we have a total number of design points, about 100. And if we implement the sparse linear model, we can retain only 10 design points among the 101. And the mean square error prediction is very close to 1 given by the functional linear model. So when you pass from 100 design points to 10 design points, finally from the mean square error prediction, you have practically no loss. And for the second data set concerning the religious data, you have 700 number of design points, and the sparse linear model retains about 15 design points among the 700, and you get this mean square error prediction. So this is the first step to go towards the selection of design points and in order to reduce the dimensionality of the data. Now I will speak about sparse nonlinear regression because in the previous slide I spoke about linear modeling in a sparse way, and the idea is to extend the notion of sparse modeling in the non-parametric way. And this work is the recent work with Peter Hall also and Philippe Ledieu. And the idea is to select very few design points in the curve in order to give both a good predictive tool and both an interpretable tool for practitioner in order to visualize where are the main important design points on my curves. So here we have a vector T. What is the vector T? It's a vector of design design points. Of course, a vector very few design points. 1, 2, 3, 4. And the vector x is just the predictor corresponding to this vector of design points. So we come back really here in the multivariate frame, the multivariate approach, and we want just to estimate the multivariate regression. That means we want to estimate the regression of the response over the vector of predictors x, which corresponds to the design point that we fix here. And by minimizing a kind of cross-validation term, and by using some standard multivariate estimator for the regression function, we can get some optimal design points and also some optimal vector of bandwidth corresponding, each bandwidth corresponding with the predictor of each design point. And we implemented the sequential algorithm. That means that at the first step, we select the most predictive design point T1 hat, and at the second step, we select the second most predictive design point T2 hat, and so on. And in this way, we can compute also mean square root and so on, and we can stop the algorithm as soon as the improvement in terms of prediction error is very bad. Here, for instance, for the spectrometric curves, we have selected these 4 design points, and we can give also the point which have been selected, and the height of each bar corresponds to the mean square error of prediction is proportional to the mean square error of prediction. And at each step, when we add the predictor with a new design point selected, we improve the mean square error of prediction and up the end, the fourth. Okay, so we have here just a mean square error prediction of 1 to 0.2, and there is some improvement. Also, from selecting the number of design points, we can use the mean square error in order to get optimal number of design points. For radius also, you can implement the same algorithm, and you get 3 points here. Okay, the last idea of my talk is a very simple idea: how to combine sparse with full method, and this is mainly the main points that we have to retain from this talk. Of course, you have from one side linear sparse model, and from the other side non-linear sparse model. The problem with non-linear sparse model is that from computational cost, it's very expensive. The reduced data, for instance, takes a few hours in terms of computational cost. Whereas when you implement the linear sparse model, you have a few seconds. So the computational cost is very expensive. And the idea is to combine the sparse linear model, which is very cheap from a computational cost point of view, with the sparse non-linear model, which are very competitive from a prediction point of view, but very expensive from a computational